All right, here we go. All right, 7.6 applications of exponential and logarithmic functions. Okay, thank you. No, it just means that the file is safe to copy over now. All right, anyway, because, yeah, I have to take all the footage and upload it. All right, so 7.6 applications of exponential and logarithmic functions. We are on page 359. Page 359. All right, exponential and logarithmic equations are very essential for using in daily life. And so what we're going to do is we're going to talk about how we do that. One of the key ways we do this is in the exponential growth rate. Now, we're just going to kind of compare a couple of functions here just to kind of explain what we mean. The green line is just y equals x. It's a linear equation. Real quick, I will mention that in both this graph and the graph of your textbook, they've stretched out x compared to y to exaggerate the differences at the low end, because that's where things start getting interesting. So, like, we want to be able to see the separation, so that's why. And x. Anyway, moving on. Sorry. All right, so f of x is equal to 2x, g of x is equal to x squared, and h of x is 2 to the x. Now, real quick note on your book. They tried to color code it, but they did it wrong. Nice. So h of x is in red on the graph, and g of x is in blue on the graph. Even though their colors are backwards in the textbook. It's amazing. Because someone not math probably did the color coding. All right. So dumb. And everyone's probably like, yeah, that's fine. All right, so you'll notice that the quadratic and exponential functions look very similar at the beginning. Okay? And then as they separate, then you see the difference between quadratic and exponential functions. Okay? The key thing here is to not eat your beard. Anyway. It drives me nuts. All right. Let me see here. What was I saying? Oh. So in the linear function, each change between x values yields a same change in y values. Okay? In a quadratic function, the change increases but slowly, whereas for the exponential function, what's happening is your changes are exponential. Okay? And that's what makes an exponential function exponential, is the fact that the changes are exponentially increasing as well. One key application of this is in population growth. Now, this is not just true of humanity, although that is a population that has shown exponential growth. At the beginning, it didn't look like it, and then the last 100 years happened. The last 200 years happened with modern medicine and modern advancements. Yeah, basically. So yeah, just like all the human advancements in science are what led to that. Excuse me for a second. Okay. Anyway, it's actually a problem. But another way that this would apply is in bacteria, if we're studying a bacteria growth, or things like this. So we can demonstrate this in the lab. So this table here is actually, with this example of bacteria, suppose a dish contains 4 cells of bacteria that's very active and reproduces by cellular division every 20 minutes. Thus, after the original 4 bacteria will divide and double to 8 after about 20 minutes. These next 8 will then divide out further over the next 20 minutes, another third of an hour, doubling to 16 total bacteria. Assuming cellular division occurs over the next few hours, this process can be modeled in the following chart. That would be horrifying. Yeah. This is the problem with bacteria. Yeah. Because we put 4 in the dish. Yes. Cool. All right. So what ends up happening is it ends up following this equation that we see here, where, oh goodness, I forget which one's which. A is the original population, R is the rate of growth, D is the frequency of growth, and T is the elapsed time in hours. Okay? That time may be based on the different problem. But anyway, notice that this function is merely a model for this phenomenon and is not exactly the same as an actual bacterial growth. There are 2 major reasons the model must be viewed as inexact. First of all, the model is a continuous function. In other words, any positive value of t may be input and any positive f may be obtained. But bacterial growth is discrete. So for example, you can't get 1.5 bacteria. In the previous example, notice that the prediction of bacteria after 30 minutes is 11.3 bacteria. Of course, that's impossible, seeing as we'd have like 11 or 12. We'd probably say 11. The second source of error in the model is that the bacteria do not divide on schedule. It's not like, they have little watches. Okay, it might be 18 minutes, it might be 22. It's 20-ish minutes. However, they provide very reasonable estimates, which is why we use them. Okay, so example A. A certain form of bacteria doubles every 2 hours. If a sample begins with 6 bacteria, let's write a function to describe the population at time t. All right, so let's go ahead and figure this out. So first of all, what is we have our model here, our population growth equation. So we have f of t is equal to ar dt. All right, so keep in mind then that f of t at this point will be the original population, which is 6, times the rate of growth. Well, it doubles, right? Okay, so that's going to be times 2. All right, and then the frequency of growth. Well, if it doubles every 2 hours, that means we would, hold on. Okay, so your frequency of growth, Siri, no one asked you. All right. So your frequency of growth is equal to 1 doubling every 2 hours. Does that make sense? So it's going to be 0.5 t. Okay, makes sense? So that's going to be the idea. That will be our model. Okay?
Question.
Yes.
Wouldn't there be an issue since it's bacteria, right? And it's doubling every 2 hours. So you're probably not having a lot happen after the first hour, but when it gets the second hour.
Again, this is part of the whole, they don't follow a schedule exactly. We know it will, by the end of 2 hours, it will have doubled. That's basically how we word that. All right, whoops. Sorry, there's a part B. Find the population at t equals 5 hours. Well, we just plug in 5. So f of t is equal to 6 times 2 times 0. Or to the 0.5 times 5. So you'll get 2.5 as an exponent. All right, 2 to the 2.5 times 6 gives us about 34 bacteria. We say 34 because the actual answer is 33.94. No. So 34. Okay, we just round to the nearest whole. All right, make sense? Another example that can be done is compound interest. There is a simple interest formula where I equals PRT. That's where the interest is equal to your principal times your rate times your time. To find the total amount, here we would say that A is equal to P plus PRT, A being your amount in the balance, okay, in the account. We just don't use that version a whole lot for whatever reason. Compound, we can have that formula. Notice it is an exponential function because you're paying interest on your interest. So each change is getting that compounded impact. We can also just compound it continuously. Realistically, if it's compounded at all, it's about the same. But compounded continuously is where we really don't want to do the math. So we use this. Okay. Use the E button on the calculator. Do not use the approximation for E. Okay, that's kind of the whole point. Okay. So we're to find the final amount of a $1,500 investment that earns 6% annual interest for 18 months. Okay. So first of all, simple interest. Okay. We know that the interest would be I equals PRT. So you just do 1,500 times 0.06 times 18 months. I'm going to assume we all can do that. And my interest would be $135. Okay. Which would mean my new amount is equal to 1,500 plus 135, so we get 1,635. Okay, so that anything higher than that is a good deal. Make sense? All right, so if it's compounded annually, basically the way we would plug this in is my new amount would be 1,500 times 1 plus 0.06 over 1 times to the 1 to the 1.5, because again, we're plugging into that formula P, the principal times 1 plus the rate of interest divided by the number of points of interest. Well, if it's compounded annually, it's only going to get 1. You can't plug in a 1.5 to this. To the nth power times t. So it's 1 time 1.5 years. Okay? Keep in mind, time always has to be in years with interest, no months. Okay? All right, so when we do this, we get that it's about $1,637.01 to find the interest used to just subtract 1,500. So it's 137.01. All right, couple bucks extra, not a whole lot. Okay. Compounded monthly, on the other hand, this starts to get interesting. I did not leave myself enough room on the slide.
Wow, SMH.
I kind of had a feeling this would be a problem.
No, I want to compound continuously account.
Notice that the only difference is our time changes from our number of times per year. That's how that's worded. Number of compounds per year has switched from 1 to 12 because it's not compounded annually anymore. All right, we get that this is about $1,640.89. The more you can compound it, the more money you get. Okay? Again, it's not a drastic difference, but it's enough. We're like, I'd take it. All right, compounded daily. All right, you'd have A is equal to 1,500 times 1 plus 0.06 over 365. 365 as my power. 1.5 is going to be about $1,641.25. If it's compounded continuously, I don't know why I did parentheses there, like just to be clear. Okay, we use the natural number e as our base, and we get $1,641.26. Okay, you notice that being compounded continuously, it really doesn't do that much compared to daily. I mean, daily doesn't do that much compared to monthly. Monthly is kind of your biggest jump from annually. Annually is the biggest jump from simple interest. So those are where the big jumps happen. Anything after annually compounded, you'll pretty much be fine because the difference gets into pennies. Now, the previous example demonstrates that the continuously compounding interest represents the greatest amount of interest that can be earned on a given principal, interest rate, and time. A graph makes this point clearer. The curve on the following graph represents a different compounding time according to the legend on the graph. That's in the book. They didn't really do a great graph, so I didn't care. Notice that although the simple interest never grows any faster, the compound interest formulas all eventually increase rapidly upward. The exponential curves and the simple curve stay close to one another until just before the vertical grid line to the right of the y-axis. This delay in rapid increase causes some to stress the importance of investing early for the retirement. The grid line where the rapid increase begins would represent the 10-year mark. Beyond 10 years, an investment account starts to grow very fast. Okay, this is why they push investing when you're young. Because there's a long time there where it's just sitting there. It's just sitting there and it looks like nothing's happening. After 10 years, it takes off because it's an exponential function. Okay, so that's really what you're looking at. Note also that the two compound interest curves stay very close together until after they have exited the portion of the graph shown. While each compounding interest scenario greatly outpaces the simple interest, it takes far longer, at least 40 years, before the individual compounded interest lines separate significantly from each other. So again, like I said, after annually, as long as you're in that category, you're not going to notice a huge difference unless it's a very long-term account, like it's for your grandkids' retirement or something like that. You know what I mean? Like, then it would matter. But beyond that, meh. The previous problems included only a simple evaluation of the given functions. Given a time, find a quantity. The following applications involve solving for the time or rate that will yield a particular desired quantity. So, for example, I want to be a real unrealistic and say I've got $4,000. I want to make it $10,000 in 2 years. I know, right? All right. So, my goal is to find the interest rate I would need to find. Okay. GameStop. No. That's the other way. All right. Anyway. No. GameStop stock. You're right. Okay, we're moving on. This is derailing. All right. So this is compounded annually. So A is equal to. Why did they use E? Oh, I wrote the problem down wrong.
Wow. Oh, continuously?
There, fixed it. You should know them. Probably. Enjoy. All right, A is equal to PERT. Okay, so I know I want this to be 10,000. I'm going to put in 4,000. E is its own number, so we don't plug anything in. The rate is the thing I'm trying to find. Time is 2 years. So first of all, we divide both sides by 4,000. We get 2.5 is equal to e to the 2r. Take the natural log of both sides. We get the natural log of 2.5 is equal to 2r. Divide both sides by 2. We find that r is equal to half of the natural log of 2.5, which is about 46%. You're not finding that, to be very clear. I mean, who doesn't?
You should just invest in GameStop.
Yeah, especially not with current banking. All right, anyway, so that's why it's very unrealistic. All right. Newton's law of cooling, it looks like this. Okay, notice even he's telling, even when the math is telling you to get wrecked, you know you have a problem. All right, I have to make that joke at least once. When an object is placed into an environment whose temperature is different from the object, the object in the environment will change temperature until they are at the same temperature. For example, when a hot piece of metal is placed in a bucket of water, the metal gets cooler and the water gets warmer. In this physics, this concept is known as heat transfer, and we've talked about this. Suppose, however, that the hot metal is placed into a room instead of a bucket. The room is so large that the metal will likely not significantly affect its temperature, especially if you have AC or something. This simplifies the problem. Newton's law of cooling gives a formula for finding the temperature of the metal object T minutes after the object is introduced into the room. The temperature T of an object, T minutes after it is moved to an environment at temperature R, is given by this formula, where T0 is the initial temperature of the object and K is the constant related to the cooling rate of the object. Now, in this formula, R is used because it typically represents room temp. Okay? So that's the reason for that. The cooling constant K will differ based on the composition of both the object and the atmosphere surrounding it. When this constant is not given, then one temperature measurement besides the initial temperature can be used to determine the constant, but we're not doing that. Okay. So example 7.6d, find the room temp of... Huh? Hey. I'll give you equations you guys need, don't worry. I'm just messing around. Find a room temp of 150 degrees Fahrenheit object of a 150 degrees, moving on. 25 minutes after it is introduced to a room that is 70 degrees Fahrenheit, assume the cooling constant is K equals 0.054. All right, so my temperature at this given time will be equal to R plus T0 minus R to the E to the negative KT. All right, so the time at 25 minutes, okay, is this a time in minutes? I'm looking it up. Yes, T is in minutes. Okay. So that's equal to the room temp, so that's 70, plus temperature of the object, which was 150, minus the room temp, which is 70, e to the negative 0.054 T, which is 25. All right. At this point, it's smash buttons on the calculator, okay? And we get that T of 25 is about 91 degrees Fahrenheit. Warm to the touch, cool enough to cool, or to touch. I mean, bleh. Warm but not gonna burn you. All right, example E though is, let's say we want to know how long it takes to reach a specific temperature instead. This problem is essentially the same, except we're looking for a temp, not a time. Well, no, we're solving for time because we're given a temp. Sorry, I'm saying that backward. All right, so I know I want my temperature to be 75 degrees. Okay, this is going to have to then equal the room temp plus 150 minus 70 degrees times E minus 0.04. No, not 0.054. Sorry. Numbers aren't important. Times an unknown time. Well, this is naturally going to involve logarithms because I have the natural number e. So let's get it isolated first. When we do all the algebra to isolate it, we get 1/16 is equal to e to the negative 0.054 t. Okay? I'm not going to go through all the other stuff because we're running short on time. All right? Take the natural log of both sides, so we get the natural log of 1 over 16 is equal to negative 0.054t. So we find the natural log of 116, divide by negative 0.054, and we find out that t is about 51.3 minutes. That's how long it would take to reach that temp. Make sense? Newton's cooling law is an example of exponential decay, an exponential function where the output values decrease as input values increase. Other scientific topics also exhibit exponential decay. In fluid dynamics, the height of the water in a container gets lower over time as it flows out a hole in the side of the container. The water level drops exponentially. In the medical field, the amount of medication remaining in a patient's body over time often exhibits exponential decay. This is why you feel pain a lot more at the end of after you're coming off the medication than when you were first on it. Radioactive decay is an example of exponential decay in nuclear chemistry. We're talking about that now. The radioactive substance has a half-life. The time it takes to change one half the mass into another substance as time passes. The mass of the original substances decreases exponentially, which I've actually shown the radioactive decay one here because it was really easy to grab the graph from chemistry. That's my reason. All right, another example of this is sound intensity. Sound intensity is actually a logarithmic scale. It's an exponential decay scale. Because as sound leaves a position, if you double the distance, it doesn't double the diminish of the sound intensity. It actually gets quartered. It's exponentially gone. So if someone's 4 times away from me versus a reference point, it won't be 4 times weaker. It'll be 16 times weaker by the time the sound gets to them. Hence why microphones are necessary and microphone placement matters. There's a big difference. Sorry for the noise this is going to take. There's a big difference between a speaker wearing it here versus here, because sound intensity is that drastic of a change because it's exponential. This is why lapels are like this. This is why you get mics where you can actually get it like right next to the mouth. This is why singers, especially those doing deep bass, will often be nearly swallowing the mic because it's hard to get an intense sound out of it. So in order for the mic to pick it up, you got to put it right next to the source of the sound. Whereas sopranos, you have no problem because those frequencies are easier to get into sound intensity out of. That's a whole concept of pitch. I'm not getting into that. But basically, our ears actually don't pick it up based on sound intensity, though. We pick it up based on sound intensity level. Okay? We don't hear the difference like that. We hear it in a logarithmic scale. Okay? So we actually have to take the log in order to know our change in things. This is why things are measured in decibels. Okay? We could measure them in bells, but then we have to use decimals. If you use decibels, 1 decibel is about the difference in hearing that you would notice that there is a difference between volumes. Okay, so it allows us to be really easily reference something that we experience humanly without having to resort to decimals, which is really nice. Okay, so this is the sound level or loudness. Sound level is called loudness. Sound intensity is the watts per meter squared. You can see the intensities listed there in table E. But then the threshold of hearing is at negative 12 decibels, I think. No, negative 120 decibels. I'm sorry, because we multiply it by 10. So anyway, more information about that is in physics, but I got to get going. So example F. What is the sound level loudness of a sound with intensity 3 times 10 to the negative 7th watts per meter squared? Watts per meter squared. Well, we just know that our sound level will equal 10 decibels times the log of 3 times 10 to the negative 7th watts per meter squared over 10 to the negative 12th watts per meter squared. The 10 to the negative 12th is the threshold of hearing. That's our 0 point for the decibel system. That's why we always base everything off that. When you shove everything in the calculator, okay, we get about 54.8 decibels. Okay, so you'd probably hear it as about 55. Example G. By the way, it's a really good thing the hearing is like that. Really good, because, wow. All right. On August 27th, 1883, the loudest sound ever recorded by humans was created by the eruption of a volcano on Krakatoa, an island in Indonesia. About 100 miles away, the sound level loudness was measured to be 180 decibels, which causes permanent damage. 100 miles away. Yeah. This is still louder than than our nukes have been. Yeah. All right. What was the sound intensity experienced at this location? Okay, so we know the loudness. We want to know the intensity. Keep in mind, permanent damage to hearing or physical damage to ears is anywhere between 1 in 10 to the 1 or 1 times 10 to the third watts per meter squared. Okay, keep that reference point in mind. So I know that beta is equal to 10 decibels times my intensity over my initial intensity, which is the threshold of hearing. Okay, I have all this information. I'm looking for I. All right, so we have B is 180 is equal to 10 dB. Oops. Sorry, B is capitalized. Of I over, whoops, I have no idea what just happened there. It's 10 to the negative 12th watts per meter squared. Okay, solving and rearranging. Okay, again, I'm assuming y'all can do algebra. I is equal to 10 to the 6th watts per meter squared.
And what's the permanent damage?
If it's a positive exponent, like at all.
Oh.
Yeah.
Ah.
Yeah.
Pretty cool.
Yeah, and also like, yeah, deafness was kind of common after that in that region.
Dude, that makes sense.
Yeah. Yeah, no, you don't want to be around that.
No.
All right, homework tonight is practice 7.6 green. Chapter 7 review is due on Friday as well, just because I'm not going to stream anything about that because, do your work. So I'm just announcing it now. Green assigned, non-green bonus, same as always. These practice problems are due tomorrow, though, to be clear. Also, test 7 will be Monday and Tuesday. You guys good?
Yeah, can you go back to the one problem that you were showing about the bacteria?
Yeah. Give me just a second.